Hi, Dr. Lyons here. In this video, I'm going to analyze a bucket pump. We're looking for some measurements of the efficiency of a bucket pump. This is a bucket pump. There is a bucket and there is a pump. The pump primarily consists of a hollow tube, which you can see the top part sticking out of the bucket here. The bottom part is submerged below the water level in the bucket. In the pump there is a piston, and you can see the top of the piston rod pointing out right here. It's attached to a lever which we move up and down to lift water out of the bucket and have it discharged through this exit port or nozzle. This is our model for our bucket pump. The black tube you can see is here with the discharge at the top. The piston right now in my model is below the surface of the water, so when the piston rod is lifted, the piston pushes the water up and out the discharge, and as the piston rod moves up, water is also drawn into the intake. Now there's a flapper valve on the real bucket pump so that when the piston is pushed down, water can flow the other way, and you'll see how that affects some of the analysis later. Now, when we're talking about the efficiency of the bucket pump, we really have two questions. One is, what is the volumetric efficiency? And that means how much water can I get out with every stroke? And the other is the energy efficiency. And we're going to do the analysis on both of those. The first question is, what is the volumetric efficiency? What is the volumetric efficiency of the pump? So the efficiency is represented by the symbol eta with a subscript V for volume, and that is the actual volume displaced divided by the theoretical volume displaced. The actual volume displaced or dispensed divided by the theoretical volume displaced by the pump. So in terms of variables, eta sub V is VA over VT, the actual over theoretical volume. And the reason the efficiency is never going to be bigger than 1 is that the actual volume is always going to be less than the theoretical volume in a real pump due to seepage. What do I mean by seepage? What I mean by seepage is that as the piston is raised and water is pushed up out the discharge, some of the water seeps around the edges of the piston and also through the valve that's in the piston of an actual pump. So we have to figure out in a lab setting how we might determine the actual volume of water displaced and the theoretical volume displaced. So it's like any engineering problem, we usually will start with some sort of model or sketch. And so here is my model of the pump. Leaving that part right there open so that we see that water can come out through there. Here's the water level. My piston is inside of the pump, and I'm going to first show it below the water surface. Piston rod comes up. That's sufficient right there. I don't need to draw the lever. And the cross section, the piston in our particular case has a cross-sectional area which is circular, and there's a thickness to the wall, and what we're interested in is the water inside the cylinder, so that's going to be the height of the cylinder times the cross-sectional area of the internal diameter. Our particular pump, as I said, has a circular cross section with internal diameter D. Okay. Coming back to our pump, in state 2, we've raised the piston. And I'm going to say it's raised to right here. And some water has been discharged. So here's a blob of water that's come out. And as that water was discharged, more water flows up into the inlet port of the pump. The piston has moved a distance x, or I'm going to call it S in this particular analysis. And the reason I'm using S is because that's the stroke length. We would talk about how far the piston rod has moved. And so since I'm going to assume that the piston rod doesn't stretch significantly when we pull it up, so that the distance that the piston moved is the same as the distance that got to get that right, that the piston rod is actually moved. So this S is the distance from the top of the piston surface in state A to the top of the piston surface in state B, or the distance from the center of the piston rod's joint to the same position, or the same distance in position B. Okay, so what do we need to do? We need to measure the volume of the water that comes out of the rod with every stroke. So we will capture the water in a cup and weigh it with a scale. So we have a scale available. We can calculate the amount of water by the actual mass discharged divided by the density of water. And I'm going to write that symbolically as M sub A over rho. Where rho is the density of water. And if I remember right, that's about 1 gram per cubic centimeter. Or if you're using U.S. customary system, it's 1.940 slugs per foot cubed. So that's straightforward. We just pump water and we measure how much comes out. What about the theoretical volume of water that could have been displaced? Well, we're talking about a cylinder of water, and the volume of a cylinder is the area times the height, if it's a right cylinder, and so that's area times height. So in our particular case, since it's a cylinder, the area is pi d squared over 4. So the question is, for this particular case, what is the height of the cylinder of water that's removed? So before the piston is lifted, I have this much water in the tube, and after the pump is lifted, I have that much water in the tube above the piston. So the difference between the volume before and after is the volume as indicated by this crosshatched region here. So the height of that slug of water that comes out in its original geometry was S. So the height of that cylinder is S. So the theoretical volume is pi d squared over 4 times S. Remember, d is the internal diameter of the pump barrel. So if I was in a lab and like I might do in one of my Intro to Engineering courses, I might be asked to do a capacity study. And in the lab, I might want to pump some water. And while I'm doing that, I would measure the mass of the water that comes out, the distance that I've moved the handle or the piston rod, and the internal diameter of the piston, the pump. So then I would calculate my actual volume as MA over rho. I would calculate my theoretical volume as pi d squared over 4 times S, and my volumetric efficiency as VA over VT. Okay. I'm a little bit happy about that because I'm done with that step. Now the second question I said we would address today is the energy efficiency. What is the energy efficiency of the pump? So the energy efficiency is written as eta sub E, and that's the theoretical energy to lift the water divided by the actual theoretical energy to lift water, particular height, divided by the actual energy spent operating the pump. Symbolically, eta sub E is going to be energy sub T for theoretical energy divided by E sub A for the actual energy. So let's just do sort of a reality check here. The actual energy is going to be greater than the theoretical energy due to losses. That means that this number is never going to be bigger than 1, and that's the correct definition of efficiency. And why is that? Well, some of the energy that we put into operating the pump goes into just moving the pump parts. So some of those losses are associated with just work moving the pump parts. Moving the pump parts. So for example, the piston has some weight and we have to lift it, and it doesn't actually contribute to the water coming out. And another thing that we mentioned was the seepage problem. And then there's also friction. And this includes friction between the pump parts but also something that I'll call hydraulic friction. And hydraulic friction occurs when the fluid flows next to a surface like the wall of the pump. There's friction there. Also when the fluid has to turn corners, like at the top of the piston there's frictional losses in the fluid just associated with it having to change its velocity, and it rubs against the walls, and also additional friction when the tube diameter changes from being a large tube here to being a smaller discharge. So all those places are associated with energy losses. Okay, so let's look at our model again. See if we can understand what's going on here. Same kind of pump, water level. Piston. State B, pretty much the same, except the piston's a little bit higher. Water's come out. And still have the internal diameter D. Well, I'm looking to find the actual energy that's required to operate the pump. One thing I can do is I can attach a scale, like a pull scale or hang scale, to the top and actually measure the force that is applied to the piston rod as I pull it up. And if I know that force and I know the distance that that force is moved, I can multiply the force times the distance moved to get the actual energy. So F here is the force applied to the piston rod. And S is still the distance traveled by the piston. So we're measuring that force with a hang scale. Now, what about the theoretical energy? ET can be calculated using the potential energy equation. If I know the mass of the water that's lifted, and I multiply that by the acceleration of gravity times the distance that that water is lifted, then I can calculate the theoretical energy. So ml is the mass of water lifted. Now, please note that that is not necessarily the mass of the water discharged. With every pump. It's not the same. The mass of the water that's lifted and the mass of the water that come out are not exactly the same. The S is the distance that the piston moved, or the other way of interpreting that is the change in height of the lifted water. So saying that the mass of the water lifted is not the same as the amount of water that's discharged. So let's explore this, see if we can understand it a little bit. Okay, so I'll go back to my model here. How much water do I have to lift in order to discharge some? How much? I can see the distance that I'm lifting the water is going to be related to how far the piston moves, but actually how much water do I have to lift? Well, one of the things to know is that the water below this water here, the water below the surface of the water in the bucket, doesn't take any work to lift. It doesn't take any, because it's floating in water. It's what we call neutrally buoyant. Okay. The other thing that's going on here is that a particle of water right here at the very top doesn't have to be lifted hardly at all to get out. But the water that's roughly here in the middle all gets lifted a distance height s. So it doesn't take any work to lift this water. And it doesn't take any work to lift the water that's already at the very top. But as I lift the piston up, water is sucked in, and so it fills back up here, and some of that water has to get lifted up in the cylinder right here. So that water that I just sketched in gray used to be below the water line, and now it's above. So if we think about this, some of the things to note is that, first of all, it takes no work to lift the water below the surface. It takes no work to lift the water below the surface, because it has neutral buoyancy. Because it has neutral buoyancy. And sort of the other observation was that the volume dispensed at the top is the same as the volume of water drawn into the bottom. So the volume of water dispensed at the top is the same as the volume of water drawn into the bottom of the pump. So with these two concepts combined, our model is going to be that all of the water above the surface is lifted. All of the water above the surface is lifted. And so that little bit of water that was dispersed is made up for by the amount of water that's sucked in. So I think it's good enough for government work. And that gives us that the volume of the water lifted. Is that the symbol I used? Yeah, I'm going to introduce this symbol right now. This is the volume of the water lifted. And VL is pi d squared over 4 times L, where L, we'll go back to the model here, L is the height of the water column above the surface of the water in the bucket. So the model is that all of the water here, that much water, is lifted a height S. So the volume of water that's lifted is pi d squared over 4 times L. So I'll define L with words in addition to the picture above. L is the height of the water column above the surface of the water. in the bucket. Sorry. L is the height of the water column above the surface of the water in the bucket. So therefore, the mass of the water lifted, M sub L, is the mass lifted, is the density of water times the volume lifted, which is the density times pi d squared over 4 L. And that means that our theoretical energy is m sub L times gravity times the distance moved, which is going to look like pi over 4 d squared rho L G S. So if I was in a lab situation and I was asked to do some sort of energy study on a bucket pump, I would pump some water, and while I was doing that, I would measure the force required to operate the pump, the distance that the piston rod moves, the diameter of the pump, and the height of the water column above the surface of the water. And I would be able to calculate the actual amount of energy used from the measurement of the force required to move the rod, F, and the distance the rod moves, S. I would be able to calculate the theoretical amount of energy required to lift the water. And the constants here are going to be pi over 4 times the density of water times gravity G times the diameter squared. And the only things that you might vary in the lab situation are going to be the length of the water column and the stroke length S. So my energy efficiency then is just the ratio of ET over EA. And if I didn't make any mistakes, which is always possible, then that should be sufficient. So we are done. Thank you for watching.